Okay, time for another FRQ. Today we're looking at the 2018 FRQ number 3. It's off screen right there, but we don't need to see the number 3. It's a 12-point, 25-minute question. This is qualitative quantitative. This does not require any experimental design. And I do have the points laid out on the side of each part there. It's a rotational problem, although it's not a ridiculously hardcore rotational problem. It's a lot more just kind of thinking through what do I think should happen, and just try to map out as best as you can. So it says the disk shown above spins about an axis at its center. Student experiments reveal that while the disk is spinning, friction between the axle and the disk exerts a constant torque on the disk. So what they're saying is at the, kind of draw it in red here if I can, somewhere there on the axle, there's like a frictional torque. Someone grabs your arm and twists it, there's some friction there, right? So that friction is preventing the axle from spinning freely within the hole. The disk from spinning on the axle, because in that hole there's some sort of friction. And they say at time 0, the disk has an initial counterclockwise positive angular velocity omega naught. So in the beginning, it's rotating around this way with omega naught, and the disk later comes to rest at some time t1. So that's at time equals 0, and at time 1, whatever that is, we have omega is equal to 0. It comes to rest. So it just kind of goes and stops. So that torque is preventing it from keeping going, provides an angular acceleration, which decreases the omega, comes to rest. And they want us to do two different graphs. On the first grid to the left, sketch a graph that could represent the disk's angular velocity as a function of time from t0 until the disk comes to rest at t1. And then on the second grid, sketch the disk's angular acceleration as a function of time. So scroll down here so we can take a look at those graphs. It's just a nice simple chart that they give us where they want us to, they got a graph already has omega naught as the maximum velocity here, and then negative omega naught. Interesting that they put that there. Then the time axis here goes from 0 up to t1. It's kind of weird that they put the t1 down there, but so be it. The idea is we want to graph on this some sort of a curve or a line that represents the angular velocity. So we start with our boundaries, the things we know exist. We know that at time 0, the angular velocity is at omega naught. So put a big green dot there. And we know that at time t1, at the end, it's supposed to have stopped. So we should put a dot down there. Those are 2 points that we know of. Now the big question is, what's the connection going to look like? Is it going to be a curve? Is it going to be like a bump? Is it going to be a weird descending sinusoidal wave? We could do any sort of thing we want. So now is where we really need to think, well, what are we doing for part 2 as well? There's no requirement on any of these AP questions that you do part 1 completely, finish it, and then go to part 2. Sometimes it's a good idea to look at all the parts within a question set just to make sure if there's nothing that's going to give you an answer and then you don't have to go back and erase. So for part 2, it's asking us what the angular acceleration is going to look like. So here's where there's a little hint up above. Scroll back up again. It says exerts a constant torque on the disk. So we got those rotational versions of Newton's laws. I'm going to draw it up above the graph here. That said a torque, net torque, is going to produce an angular acceleration by the equation I alpha, where I is the rotational inertia. So if my torque is constant, then my alpha has to be constant. So we need to have a constant acceleration here. And if we think back to when we were doing, I'm going to write that in here real quick, constant acceleration. If we think back to our linear motion problems, when we had a constant acceleration, that meant our velocity graph had a constant slope because accelerations are the rate of changes of velocities. Same thing goes here for angular problems. Angular velocity changes with respect to time, that gives us our angular acceleration. And if it's a constant change in angular velocity, it's going to be a constant angular acceleration. So from omega naught down to 0, we would have a straight line, as straight as you can draw it. I'm drawing on an iPad screen here, so it's a little funky. Something like that. I'll put a little note here. Straight. So you can do that, okay? If you're taking the AP test and you crooked drawing all the time, put a note that says it's supposed to be a straight line, and they'll grade it that way. They're not going to think that this is some like 20th order polynomial or something like that. So the angular acceleration now we got to think of. We started with omega naught being positive because it said it was going in a, scroll back up here, its initial counterclockwise positive angular velocity. Well, if I'm going to be losing angular velocity as time goes by, that means my alpha has to be negative. I have to have a negative acceleration that's subtracting away from it. So whatever I decide to call it here, I'll just put a dot down here and say that's my alpha. Don't know what the value is, but it's something there. It's going to be the same alpha the entire time until it stops. And so it'd be nice straight, make that note again, straight. Straight horizontal line because it's a constant acceleration the entire time. Now, that kind of wraps up part A. Part A was worth 4 points total. You got, for A1, you get a point for having some sort of graph that goes from omega naught down to 0, and you get a second point for it being a straight line. For part 2, you get a point, I can't remember exactly what you get the 2 points for. Pretty sure you get a point for having it be a negative acceleration and a point for it being a straight line. I think those are the 2 points. But 4 points out of 12, that's a third of the points just for drawing a couple lines. It's pretty good. So it's always important to remember how to visualize these graphs. All right, part B, looks like my point structure went off screen there. There we go. For part B, it says the magnitude of the frictional torque exerted on the disk is tau naught. Derive an equation for the rotational inertia I of the disk in terms of tau naught, omega, and omega naught and T1 and physical constants as appropriate. So this is where we're going to have to dig back into this equation that I wrote down, the rotational version of Newton's second law. This is a 3-point equation. So we've got a situation where we know our omega is decreasing, and we know that's being produced by some alpha. So we've got the equation net torque is equal to I times alpha. And we have the idea, because it doesn't want alpha in the equation, it wants omega naught in time. We also have the idea that alpha is going to be some change in omega naught divided by some time interval that goes by. So we have to combine those two in order to get I equals something. Sorry, this is a morning video session. Need my coffee more than ever. So my goal is to solve for I, which means that I need to substitute in the place of alpha, all that omega and stuff. Now I just realized I put omega naught there. That was a mistake. So here they tell us that the magnitude of the frictional torque is tau naught. So that means technically it's negative because the acceleration is negative. But here, when they tell us that lets us know that we can work in terms of magnitudes as long as they're related from something down to 0 or up to 0 as time goes by. So we can say that our alpha, because our alpha is going to slow us down, and our delta omega is going to be technically final velocity 0 minus initial angular velocity omega naught. We can just call it omega naught on the top. And the time it takes for that to happen, that time interval, is the time t1. So we just substitute in the two values that they gave us. And the torque is going to be tau naught. So I can take these things and I can substitute them in, and I have tau naught equals I times omega naught over t1. And so I've got this expression here that I've replaced my alpha, and I've replaced the sigma tau for the net torque, and I've replaced it with the torque that does exist. Technically that delta omega should be negative and the tau naught should be negative, but they're saying magnitude means we have a negative on both sides. We can just drop it and we'll be fine. The last step is then to just take this and solve it for I. So we would multiply the t over to the other side and divide by the omega, and we'd have t1 times tau naught divided by omega naught. And that is an expression for the value of the rotational inertia. Not something you're going to find in a table because it's very specific to this problem. Now this is this part right here is worth 3 points. So all this equation stuff is worth 3 points to get to this final answer. You get 1 point for establishing Newton's second law in rotational form. You get a point for establishing the alpha is going to be omega naught over t, and then you get a final third point for setting it up with everything in there and then solving it for I. There is alternate method that you could use here, which is, if I'm not mistaken, I'll go ahead and write it down. I think you can also, as an alternate form, which I don't think most people probably would, but some people could, is to say that a change in angular momentum is going to be equal to, so if I'm trying to think here, we want to do the angular version of impulse equation, like fat mav, it was force multiplied by time. So in this case, we'd have torque multiplied by some delta t would be equal to the change in angular momentum, which you could say that would be I times omega, or delta omega, and then you'd have the tau naught and the t1, and you could work it out that way too. But most people, that probably wouldn't be the first thing that jumps to their head. Okay, onward. Let's see what happens next. Part C, also worth 4 points. It says, in another experiment, the student again has initial positive angular velocity omega naught at time t0, so same setup as before. At time t equals half t1, so halfway through the original experiment time, the student starts dripping oil on the contact surface between the axle and the disc to reduce the friction. So they're putting a little bloop, bloop, bloop on there to reduce the friction, make it spin easier. As time passes, more and more oil reaches the contact surface, reducing the friction even further. So essentially, you can think of it as like friction starts to disappear. When you oil some sort of two surfaces rubbing together, the oil produces a low friction surface that allows there to be, well, no force resisting motion. So the 4 points here, they want us to redraw the graphs. What is it going to look like under this new circumstance? So what's really important here is this idea that at 1/2 the original full time, which they're calling 1/2 t1, that's when the student starts dripping oil on. So prior to that, it's the same. So it's the same problem before the oil gets dripped on there. So for the graph for the omega and for the alpha, we can just kind of redraw what we had from before. So prior, there's no difference. So where's my green pen? We started omega naught. Now originally, put a little dotted line circle there, that's where we ended up. So at the halfway point, we were there. And so I'm going to draw a line to represent that omega naught has a nice linear decrease from, omega has a nice linear decrease from omega naught to half of that at half time 1. Sorry, I didn't have that bottom part of the graph shown. And then for the alpha, I had it drawn like so, and it originally was going all the way over to there, but now I'm just going to go halfway. And now I got to figure out what's going to happen for the rest of the graphs. So here you can see there's a big disparity between part 1 and part 2 in terms of points. Part 2 is a little bit easier to just kind of think about, but part 1, there's some details there. So normally I would have had the graph continue down and hit 0 for the omega. But at time half t1, the person starts putting oil on there. Now if you put oil on there, that means there's going to be less friction. So let's throw a little like idea here. So less friction. Not a bad idea to write this stuff down in your thought process. Less friction should be less torque. And if there's less torque, there should be less angular acceleration, which means that you're getting less change in omega as time goes by. So that kind of chain of thought means instead of my line continuing down and getting to 0, it might only make it to like here. It might make it only to like, there's still a little bit of angular velocity left because at time t1 it should have stopped, but if you have less friction, that means it's not going to stop as soon, so it's going to keep moving beyond that time t1 that we originally had. So next question is, what does it look like between those 2 points? Between the point that I've got right here, sorry, I should be using my highlighted cursor, and the point right here. Is it going to be a straight line there? Is it going to be a curve? The key is up here at the top. They say as time passes, more and more oil reaches. So that means as time goes by, as you go from half T1 to T1, you keep getting less and less friction, which means you get even less torque, which means you get even less angular acceleration, which means you get even less change in omega. And the least change in omega you can have is no change in omega, which means you constant speed, and that would be a flat line on the omega graph. So it seems that we should be going from whatever our slope was and transitioning closer to a flat line. So it should be curved. Something like that. Yours may be more dramatic than that, but that's generally the idea that they want to see. And that's where the 3 points come from there. You have the fact that there's a change at half T1, that's worth a point, that it's the same as it was before, but then at half T1 something changes. You get a point for having it not reach 0, and you have a point for it being that sort of curved shape, that it's not a constant change in omega as time goes by, that it's a decreasing change in omega. So that's why that's worth 3 points. There's a lot of nuance going on there. And for the angular acceleration, you get a little bit of leeway in terms of what it looks like, but you're supposed to show that at time half T1, the angular acceleration starts to decrease. There doesn't say that, I don't think it doesn't have to go to 0, but it can just decrease, and so you just draw something like this. It could look like anything, except you would want to have it so that the angular acceleration gets closer to 0. Straight line's probably better, but because you can think of it as like they keep adding more and more oil, keeping less and less torque, it's easier to think of that as a linear relationship, oil to torque. So straight line there for the angular acceleration is probably best. Next, last part. Oh, that's a lot of words there for 1 point. Classic AP tests. Like to throw in a big complicated thing and not make it worth very many points. But we'll still take a look at it and give it fair time. It says the student's trying to mathematically model the magnitude tau of the torque exerted on the axle by the disk when the oil is present at time t is greater than 1/2 T1. So the second half of our graph where it starts getting curvy. The student writes down the following 2 equations, each of which includes a positive constant with appropriate units. Which best mathematically models the experiment? So there's this equation that says the torque is equal to some constant multiplied by t, the variable time, minus 1/2 T1. So let's assume that it's half a second. So from time half a second and on, this would be the equation, or from time half a second and on, this would be the equation where that whole t and T1 part is in a denominator. And you want to say which would better mathematically model the experiment. So again, this is worth 1 point. So if you pick equation 1 or equation 2, that's worthless unless you have an explanation down below as to why. And I'll probably write the explanation up above, right next to the equations here. But here we have the idea, again, that net torque is going to be equal to I times alpha. So in the case of these two equations, does one of these equations more than the other represent what's happening to the torque and therefore maybe angular acceleration? So this could be a bit tricky because right here we have angular acceleration. Sorry, make sure my face isn't over the pictures. The angular acceleration we said was technically getting closer to zero, but it looks like it's an upward sloping line. So it's tempting maybe to look at this equation 1 and say, well, torque is kind of linearly dependent upon time, which means angular acceleration would be linearly dependent upon time. This is essentially saying torque is proportional to time. That's what that equation boils down to. You're taking time minus a constant multiplied by a constant, but in a nutshell, it's a linear equation. And then here we have torque is essentially equivalent to 1 over time because we have time in the denominator. It's time plus some constant and then divided under some other constant, but essentially it's an inverse relationship. Well, in the case of, and that constant could be a negative, it doesn't have to be, well, I guess it says includes a positive constant, C1 or C2. So in the event that we're going beyond T1, sorry, I had to pause the video, something popped in my head I need to think through again. So we've got these two different equations that could mathematically model the torque, and the linear sort of relationship here looks kind of good, but there's some problems with it. And this one looks like, I think I was talking about how the C1 and C2 had to be positive constants, and I kind of seemed to mess it up in my head, so I had to go back and take a look at what their point structure was for this. I know it's 1 point, I'm spending a lot of time on this 1 point thing, but when you're taking the test, you don't know which parts are worth 1 point or 4 points. So the limitations here, while this does look in our picture to be kind of linear, the problem is what happens after T1. After T1, it keeps increasing if it's a linear equation. And then at some point, the torque is going to go to 0, and, sorry, covering up with my face, at some point the torque is going to go up to 0 and then get bigger still. So as time goes by, the torque is going to get bigger and bigger and bigger as time gets bigger and bigger. So the problem with that, that's a bad one, is that torque keeps getting bigger. Which it's not supposed to. It's supposed to go to 0 and then stay there. But in an inverse sort of relationship, if the time keeps getting larger and larger and larger, the torque is going to approach 0. And the reason I had to pause the video and take a look is because technically the angular acceleration is negative, and in this torque equation that we have right here, if you're adding something and C2 is a positive number, then that torque would be a positive number, but it doesn't say any, I guess right here it says model the magnitude of torque, but then C2 is a positive, I don't know. Sometimes the physics 1 stuff, they try to get too simple for some things, and they cut out details that might like niggle at your brain like that one just did for me. It's like, wait a second, that can't, like neither one of these are right. Technically, neither of these equations are right unless we look at it just being the magnitude, which is annoying. So anyways, the 1 point you get is for saying that equation 2 is the correct answer and for having some sort of explanation along the lines of this to explain why equation 2 would be correct. And that's the 12-point problem. Actually, let me look real quick. You can see what the points breakdown was. All right, so according to the College Board, the points breakdown for this was average score, 6 out of 12. I can guarantee you a lot of people missed question part D here. just because it's 1 point right off the top. Bunch of people probably forgot the curving part here. Then as we go further up, I'm sure a lot of people missed the equation stuff because they probably didn't finish it. They maybe wrote down a couple of things and didn't complete it. Hoping that almost everybody got these 4 points right here, but that means only 2 points from the rest. Don't know. Okay, that's all for now.